Hello, good day, lovely people. How are you doing today? Okay, today we are going to look at branch of calculus involving calculating or determining the area under a curve. When we talk about the area under a curve, what are we talking about? If I have this graph and I'm asked to figure out the area, let's say that this is between 0 and 3, and I'm asked to figure out the area between 0 and 3. Or even the area between -3 and 0, whichever one. Now look at this. The area under a curve, if it was just pure mathematics, we will just think about the area of a basic shape. It could be a triangle, it could be a rectangle, it could be a circle, or whatever shape. But if we look at the shape, it is not a basic shape. We have the curved part here, even though these other parts are straight. So it is not easy for us to just figure out the area under this. And that is where calculus comes in. The area of irregular shapes can be calculated using calculus. So we can just do that if we want to get the exact value without having to go through anything, we use what we call the integration method. That is actually what the integration does for us. Between a range to another, the area under that curve. Let's take this. If this is a curve given as x squared plus 4, and this plus 4 means the y-intercept is at 4. We can figure out the area for this section, the exact or the actual area for this section of the graph, and mostly we use it in production and construction. And we can figure out, what do we do here? We can get the integral of the graph that yielded that, the x, from 0 to 3. So the definite integral of this will give us the actual value for what we have. Now, the actual value in this case, if we integrate this, it becomes x to the power of 2 plus 1 is 3 over 3 plus 4x. And remember, this is for the interval of 0 to 3. So our answer to this will be 3 to the power of 3 all over 3 plus 4 times 3. That is the interval, the higher interval minus, this is 0 over 3 plus 4 times 0. So this will give us the area under this graph. This is 27 over 3, which is 9 plus 12. Everything we have on the other side is 0. So the area under that graph will give us 21 units squared. So the area under that section will give us 21 units squared. So irrespective of the fact that it doesn't have a basic shape, we can still calculate the area using integration. Then there is another way of doing this. We call it the estimation method. Let's say we don't know the range of values, or we don't know the number of things here. We can actually divide this into multiple rectangles, or what we call things that look like a rectangle. Reimann is a man that first of all performed this operation. He tried doing this multiple times before we now settled for integration. He tried doing it. He said that the area of this given section can actually be determined by breaking down the section into multiple rectangles. And he said that the more number of rectangles you have under this, the closer you get to the actual value. So if you have 5 rectangles, you are further away from the actual value than when you have 20 rectangles. Because you see, if you have more rectangles, this part, the curved section of this part starts going away because you have more rectangles, and we can actually use the length times the breadth. So what we do is, the number of rectangles we have, we calculate the area of each of the rectangles, length times breadth, we have f of x, which is the y value represents the length and the x value represents the breadth. When you add all of them up together, that will give us the area of that section. Now, using Reimann, we can get a general formula that can work for any type of rectangle. Instead of going to the exact value, we can get an estimate of what we can get if we are using 5 rectangles, the value we can get if we are using 20 rectangles, the value we can get if we are using 40 rectangles. We can manipulate and then check what our margin of error is going to be in this case. And that is where Reimann comes in. What do we do with Reimann? We remember, because we are dealing with rectangles, we need to calculate the area of individual rectangle, and we don't need to deal with the exact approach anymore. Now, what do we do? The first thing, we remember that this is our f of x. Remember that f of x is equals to y. And the changes in between the rectangles, we can use the delta x. Delta x means the difference between the right and left bottom part of it. So if we have 1, 2, 3, so to get the breadth is 1 minus 0. To get the next breadth of the next rectangle is 2 minus 1, so that's why we're using delta x. So in a nutshell, the area of this is going to give us f of x times delta x. And that is length times breadth. That is length times breadth. So what do? We need to go and start getting each and every one of them. Now, instead of using f of x and delta x, because we have multiple rectangles, we know that our rectangles will go from I to first rectangle until it gets to any number of rectangles. So we use R to denote the starting point until it gets to any number of rectangles. So instead of having f of I, we can have our f of x of I and delta xi, representing any number of rectangles that will be given. So let's start. The first thing we do is to get the parts that we need to use in the sum. We get the parts that we need. So the first thing, let's get our delta xi. Delta xi, remember, it is the change in y. So we will take the upper limit minus the lower divided by the number of rectangles. Remember, in this case, we are doing it for any number of rectangles which we don't know. So this will be our delta xi. If we simplify our delta xi, we have 3 over n. Let's put it on this line, 3 over n. Then we have to get the bottom left corner, and we say that our xi will be the bottom left corner, which is the lower part, 0 plus I delta xi. And then we have our 0 is done, we have I, our delta xi is 3 over n. So we have our f of xi as 3I over n. What is the next thing we will do? Remember, we want to calculate the area. We are only working with our delta xi. So let's get our f of xi, what our length will be. If it was an ordinary function, we just plug in the value of x here, and that gives us our length, which is our f of x. So here, if this is also our xi that we are using to represent multiple options of rectangles, then we can do this. So we can work towards getting our f of xi. So in the given equation, remember the given equation is f of x is equals to x squared plus 4. So in the given equation, we replace our x with xi. Anywhere we see x, we replace it with xi. So this is going to be 3i over n. That is our xi, all squared, plus 4. Plus 4. So if we simplify our f of xi, This will give us 9i squared over n squared plus 4. That is our f of xi. Now we go on and calculate the area in terms of the number of rectangles given. So the area here will be, area of 1 will be f of xi, which is 9i squared over n squared plus 4, that is our f of xi, times delta xi. Our delta xi is 3 over n. Our delta xi is 3 over n. Now, we simplify this, so the area for 1 will be 27i to the power of 2 over n to the power of 3 plus 12 over n. That is the area for 1 rectangle. Now to check for multiple rectangle, remember you do this for one rectangle, do for another rectangle. For multiple rectangle, we think about the summation of all the rectangles as I starts from 1 to n, any number of rectangles. From 1 to n, I from 1 to n, and then we have this. So this will be repeated multiple times. When I is 1, when I is 2, when I is 3, when I is 4, and so on. So we will have 27i squared over n cubed plus 12 over n. What do we do here? We simplify. We simplify this by breaking it down. 2 sections. We deal with separate sections so that we can easily apply the formula. So let's take this off. Now, what do we do? Each section works on its own. I have as I, it starts from 1 to n for 27i squared all over n cubed plus the summation of 12 over n. Now we simplify each of the branches again. Remember here is also I to 1 from 1 to n. Now, as we simplify, we think about the values. If this formula will be given of I squared, n, and the rest of them. So all these will be given. So we go on. If we go on here with the first one, let's take out anything that will not form part of the values, already established values. So we have for I equals 1, and then we have I squared. Why are we using this? Because this is a predefined value that we use to simplify under Reimann sum, which will be given in your formula sheets. So we go to the second one. We also take out 12 over n. If we are taking out 12 over n, for I equals to 1 to n, we have 1. Remember, 12 over n times 1 is 1. 1, the summation of 1 is predefined. Now we go to the formula sheet and pick out these values. Now I squared from the formula sheet is n cubed, so we replace it. So we will have 27 over n cubed, and summation of this, the whole of it. The whole of it will be replaced because it has been predefined, the same thing to this. So we will replace those. So 27 over n cubed, the summation of I squared as I stand from 1 to n will be n cubed. So we replace with n cubed over 3 plus n squared over 2 plus n over 6. So this is for this. And then we go to the next one, plus 12 over n, and then summation of 1 is n. Remember, we are working for n number of rectangles under Riemann sum, and this will give us an estimate that we can use to check for even multiple rectangles. So it can go on and on and on depending on the number of rectangles that was applied. So here let's simplify. 27 times the first set will give us 27 over 3. 27 times this plus 27 over 2 n squared. Remember, we are doing distributive. Okay? 27 over 2n. Because n squared will cancel, n squared we are left with 1n. Plus 27 again, we have 27 over 6 n squared. Then here we have plus n, we cancel out n, plus 12. So this will be the area, the formula for area for n number of rectangles. We can simplify it further and collect like terms like 27 over 3 plus 12, and that will give us the Riemann sum for n number of rectangles. So let's check this. I have 27 over 3 is 9 plus 12. 9 plus 12 is 21. 9 plus 12 is 21 plus 27 over 2n plus 27 over 6n squared. So this is the formula for Riemann sum that we can use to figure out the area of n number of rectangles for the given expression, which is f of x, x squared plus 4. Now, can we get an actual value here? Yes, we can get actual value. But this is the base from Riemann sum. So what we do here is, if they're asking for 10 rectangles, we replace n with 10 rectangles and use it to check the margin of error based on what we have gotten from the exact value. If they are asking for 50 rectangles, if you do this iteration, if you continue to check, you will see that as you increase the number of rectangles, you see that you are also getting closer to the actual area, which we used integration to get previously. So as you continue to increase the number of rectangles, your margin of error becomes smaller and smaller and smaller. So this is an experiment performed to check what happens when we use multiple number of rectangles to determine the area under a curve. And this area is an approximate or an estimate of the area. But remember, what the difference between this and the other one is that we just get the exact area, but this we can also check and say, if we use 2 rectangles, what will it give us? If we use 10 rectangles, what will it give us? And we continue doing this until we get closer to the actual area. Now, what do we do if we want to just calculate for any number of rectangle? For any number of rectangle, that is the last space here. For any number of rectangle, it means that our rectangle can grow and grow and grow until infinity. It can become infinity. So what we do is we take the limit of the function as n number of rectangle tends to infinity. The limit of that function as it tends to infinity. So it's the limit of 21 plus 27 over 2n plus 27 over 6n squared as n tends to infinity. If you plug infinity here and here, you will see that the limit of this function will give us 21 units squared. Remember, this is when the number of rectangles is uncountable. When the number of rectangles is uncountable. If you check from what we did previously, under integration we got something like this. So please, when you're writing, you must check if they're asking you for Riemann to use Riemann sum, Riemann sum must be used. And Riemann sum returns approximation of the estimation. If they're asking for the exact value, then they are asking you to use integration on the given function. Use integration on the given function and you get the exact value of the area under the given curve. Remember, it can also go to another thing. They can ask you for enclosed area between two graphs. So I can have this graph and this graph. It can also be done using integration. If I'm being asked for this enclosed area between two graphs, a linear graph and a parabolic graph, it's not also a basic shape, but we can also figure this out using Riemann sum or using integration. It is the same approach. The same approach all through. Get delta xi, get f of xi, get the area which is f of xi times delta xi, and plug in the predefined formulas for when you are getting the summation of the values, and get the general formula for any number of rectangle. And if you want to take if you don't know the number of rectangles, that means it tends to infinity, then you can plug in and get the value. But this is where we need to understand for Riemann sum to stop. And any number of rectangles mentioned can be plugged. So this is Riemann sum. Please, if you need additional clarity, ask question under this video, and I am here to help you, to give you more clarity, or even to provide another equation and use it to solve this problem to give more clarity. Thank you for being here, and do enjoy the rest of your day. God bless you.